Okay, thanks for invitation once again. My name is Piotr, and today I will present this most recent paper of ours, the sparse frontier. The paper is about sparse attention. In this particular case, about training free sparse attention. My background with sparse attention spans before this project. This project lasted for a year. But one of the motivations to start these projects is actually that we finished our past project, which was about trainable sparse attention. And then the field of sparse attention got very, very popular. And there were so many papers, and we were actually amazed by the fact that plug-and-play approaches, that basically you can train a model with dense attention and then add some sparse approach that is 5 times faster on top of the pre-trained model with dense attention. It worked amazingly on the evaluation benchmark that were used by the authors. We were amazed by the fact, and we decided to spend some time, and we spent a year to better understand what's going on, to understand the core differences between sparse attention methods, to understand their limitations, to thoroughly evaluate them, and also to maybe understand what's the future of long context models, the role of sparse attention in it, and research problems involving sparse attention for the future. Reza, I think you're unmuted. Can you mute yourself, maybe? Okay, thank you. Okay, but this I made a small assumption that sparse attention is important. So why it is important? Basically, I would say that it's unquestionable that long context processing in LLMs is important. For example, I guess many people right now are using Cursor, and it's still an issue that in large code bases, it's very important for Cursor and LLMs to produce the right solution to the coding problem, to add the right context. Sometimes we need to filter it by ourselves because we cannot fit entire code base into an LLM because then it doesn't work. So we need to filter manually and attach as a context right files. And this is time consuming. Sometimes we jump into a new code base and we want to add some functionality, and we want LLM to do it by itself. However, it's not the case at the moment because of two reasons. First of all, current LLMs are still not perfect in terms of long context, and this is probably the data issue, lack of data. However, the second main issue is that it's very expensive. The evaluation, the inference of LLMs right now for long context splits into these two phases: prefilling and decoding. Prefilling processes the input, the prompt, all the context that we put into the model, and the complexity of this phase scales quadratically with the sequence length. So for very long sequences, it actually becomes a bottleneck. Then we have decoding, where LLM generates the answer to our problem. During this phase, we have another two issues. First of all, to be able to generate efficiently, we have to store past representations of the past tokens, that is KV cache. These grows linearly, causes a huge memory load. Also, for every generation step, we need to load this KV cache from memory, and these bottlenecks the generation. So generally, self-attention causes the long context processing to be very expensive. And one of the most natural solution for that, given that the attention is problematic, is to propose a more efficient variant. So the core idea is that we don't need to compute everything. Instead of computing interaction between every query token with every key token, let's just compute only a subset of those interactions. We don't know which ones. I'll get into that. But the core idea is that we can only compute a small subset of interactions and still get almost the same output. So sparse attention will affect both of the bottlenecks I mentioned, both during prefilling and decoding. So that's the general idea. So as I mentioned, basically over the past 2 years, but basically over the past 10 years since self-attention has been proposed, so many different, more efficient variants have been proposed. And recently, I think over the past year, more than 100 papers have been proposed, different variants of sparse attention. And one of the core issues that I realized when I was researching and doing my literature review over the past years of all those approaches is that we don't really know if it works. What I mean by that? Of course, when you propose a new paper, a new method, you cannot evaluate on everything. However, the issue is that let's say that a new paper comes out and they only evaluate themselves on needle in a haystack. So like very synthetic input, the simplest possible task where we clearly specify what we want to do. From a very long input, we need to retrieve only a certain part. We don't need to process it, only to copy it from the input to the output. So it's absolutely the simplest possible task. If the evaluation of a new method only is on task like needle in a haystack, then we cannot really infer what would happen if we apply this method to reasoning models, on math questions, on code, or something that's more difficult. Even tasks that involve natural language, like summarization, like imagine, so that's the first thing. So like that sometimes the evaluation is very simple and synthetic. The other thing about the evaluation is that we have those so-called task categories. We don't really know how to like assess the difficulty of an input. For a simple category that we will call code, a code question could be either what a given function named like this in this file does. So this requires the model to retrieve only a single function and then summarize what it does. On the other hand, if the question is, what would be the output of a multi-file program for this given input, then the model has to retrieve everything from very long context, understand the dependencies over the functions, and also simulate the execution of this code to understand what output it produces. And both of these questions are actually like single question code inputs. So this is a very high-level categorization. We cannot really, for many benchmarks that there are and are used for evaluation, they are not controllable. Controllable in a sense that we cannot control the input, the difficulty of an input. So that's an issue. Because we cannot control those things, we cannot really also infer how a model with sparse attention will perform on more extensive evaluation on different tasks that we care about. The second thing is that transformers are very black box models, and to the best of my knowledge, all training-free sparse attentions are based on different forms of heuristics. For none of them, we cannot really estimate what would be the maximum degradation in performance if we apply this sparse attention with a given compression. So first, how we tackle that in summary. First of all, we have reviewed different papers that studied what makes long input difficult and also what makes an input difficult for different sparse attention methods. So in short, this is whether an input is in natural language or whether this is very synthetic input. Also, the self-attention mechanisms display different patterns for different task types. Also in our approach, we very much control for the sequence length. So we've also run controlled studies to understand the impact of the sequence length on the sparsity of different models. Second of all, to be able to assess how robust those methods are, we introduced a statistical framework to measure maximum sparsity that we can use so that we preserve dense models performance. So this is how we tackle the general problem of we don't know if it works. Second problem with, like, as I said, over than 100 papers over the past year is we don't know why it works. Although I can spot many similarities between the papers, there are so many low-level choices that has to be done. And you cannot, of course, compare against all other prior work. So it's sometimes difficult to understand whether using longer local window gives you the performance, or that you have estimated what to compute this way or the other way, or how many attention sinks you've used. So like those low-level choices sometimes make it difficult to understand for someone who wants to use and adopt sparse attention to their model, like what is really crucial and what they should focus on. So we spent quite some time to understand what are the key differences between the methods. So we wanted to build some kind of abstraction to understand what are the core choices. We came up with these 4 key design choices. That is the choice of unit of sparsification, import how we estimate what to compute, how we allocate budget across different layers and heads of the model, and how our sparse attention method manages the KV cache. I will, of course, discuss all of it in detail. We have decided to choose 6 representative patterns. We have unified their implementations, and therefore this allowed us to run systematic ablations to understand what is important, what is crucial, which design choices are the most important, and for good performance. This is the end of the introduction. So in short, the main research questions that we tackled in this work are, first of all, given a fixed computing budget, we asked whether one should choose a small dense model or a large model with sparse attention. So this is the analysis akin to scaling Gauss papers. Which one's more efficient? Whether even using sparse attention makes sense. Second is how far we can actually push sparsity while making sure that our model is robust and can perform well across different various inputs. Third of all is analysis of different approaches of those key design choices and understanding and trying to understand when a given choice is better for what types of task. So now let me discuss. Let me try to give you an overview of the space of sparse attention. So in short, sparse attention, as I mentioned in the beginning, the main goal of it is to compute only a subset of query key interactions, therefore speed up both prefitting by reducing the number of operations, or decoding by lowering the memory transfers and loading of the KV cache. We want to make the best possible approximation of the dense output. We have 2 metrics to assess the speed up that correlate with the speed up caused by equipping the model with sparse attention. That is sparsity, and this is the ratio of skipped interactions, which are not computed, or compression ratio. Basically, it's the easiest way to understand that is by example. So like 90% sparsity produces 10 times compression. Basically, compression should correlate with the overall speed up of the execution of the sparse attention. The four axes on which the attention differs, the key design choices, are first of all what will be computing. So we have our square attention matrix that we'll be trying to approximate, and we'll be either computing blocks, we'll be computing verticals from this matrix, we'll be computing slashes. Importance estimation. So whether our pattern, what we'll be computing, is input dependent, is content aware, or we'll be computing the same thing for every possible input. Then it's budget allocation. So whether we will compute the same portion of the attention in each layer in the head of the model, or we will split the budget, allocate the budget non-uniformly. And the final design choice is whether we'll keep the full cache or save some memory by throwing out some of the tokens from the KV cache. So first, let's discuss the first two, because I believe that these two are the most important. What I believe is the main challenge of sparse attention is that attention maps, this has been proved by many works for long context inputs, are very sparse. However, they are also very irregular and difficult or even almost impossible to predict. What the attention map will be, how it will look like. It differs across tasks. It also differs within the model across different layers and heads. It's all very dynamic. So, like, given the wide variety of possible inputs, like, how do we really decide what to compute for a given input? Like, that's the main challenge. Imagine like the simplest possible approach, and this is actually like one of the first approaches that were proposed. So we have observed this type of attention maps where the yellow parts are the interactions with high attention scores, so those interactions which are deemed important. So let's assume that we will we'll propose a fixed pattern where we will compute some portion of the sparse attention matrix corresponding to the local input of each token. So how to determine the optimal size of this local window? Based on this input, it could be very short. So we could place a line here, and we will get a very good approximation. On the other hand, for this type of input, we would need to place the line here, because otherwise we will skip some very important interactions. On the other hand, if we place the line here, then this type of line won't be really optimal for this attention map, because we'll be computing a lot of irrelevant stuff. Actually, even for this map, if we compute all of these, then we'll also be computing many interactions that are theoretically not that relevant. I mean, all those triangles. So yeah, I think that this kind of illustrates the problem, because ideally we would only compute those interactions. But how do we find out that these interactions will be important? How do we understand? How do we estimate that these interactions will be important, and how we do it efficiently? So that's like the main challenge.
Just a quick question here. So these are the figure on the right, the green patterns. Are they the dimensions of the particular matrices that you are?
Okay, so basically, sorry for not describing that. So basically, what I'm plotting here is the attention scores, the real attention scores for some input during prefitting. So like on the x-axis are the queries, on the y-axis are keys. So basically, the yellowish green parts are those interactions which get high attention scores, which are theoretically important to compute.
Yeah, okay, thanks.
So yeah, if we had to come up with a heuristic for this type of maps, and this heuristic is, okay, compute some local window, and we need to determine what size of the local window we should compute. This is difficult because those attention maps really differ across inputs, attention heads, attention layers. So how do we do that? How do we know how to compute? Cost of the dense attention is quadratic with respect to sequence length. And cost of sparse attention will split into two parts. That is cost of the sparse computation itself, once we know what to compute, and cost of what is called in the literature of index building. And that is estimating what we need to compute, which parts we need to compute. So let's go for it very slowly. It's like, I think it's one of these slides that one of the slides with the most amount of text, but this is really important to understand. So let's assume that for each query, like and there are n queries, we will compute a fixed number of interactions k, and k is much lower than n. Then the cost of sparse computation is n times k. But we'll also need to account for the cost of understanding, estimating what to compute. And this cost has to be lower than n squared. It's trivial when I say that, but basically it creates a very important limitation, because ideally, like in this past example, like you could ask me, like, why cannot we like estimate how important every possible interaction is, and then like take top k and only compute the top k most important interactions? So we cannot do that for every possible interaction, because estimating the importance of every possible interaction costs quadratic amount of time. And basically, this will diminish any gains from sparse attention, because estimating what to compute basically equals the cost of computing the dense attention itself. So also we will need to efficiently estimate what to compute. And this is a limitation for the design of sparse attention. So, as I mentioned in this prior slide, we cannot estimate the importance of what to compute for every pair of individual query with every possible individual key, because it will require quadratic times. It will generate the quadratic estimation cost. We will need to somehow increase the granularity of this estimation. So to do so, to lower the cost of estimating which parts of the large quadratic attention matrix are the most important to compute, we will chunk the attention matrix into blocks. So we can either consider, so basically we have 3 different possibilities for queries, 2 different possibilities for keys. So the first option that we have discussed already is picking individual queries for individual keys. We cannot do that because this involves a very high estimation cost. On the other hand, we can, for example, create representations for chunks of queries, and then for each query chunk, we can estimate which chunks of key tokens are most important for this chunk of queries. This will basically lower the cost of the estimation to n squared divided by the size of the chunk squared. And this will make it way more efficient. So basically what we are trying to do is we are trying to lower this estimation cost. What we can possibly allow for is chunk of queries attending to individual keys, chunk of queries attending to chunk of queries attending to the individual keys is also very popular. This type of pattern is called block sparse. So basically, we'll split the original matrix into blocks and then estimate which blocks to compute. Also, popular patterns try to estimate important keys or important chunk of keys that are shared across all queries. And all of those limitations, so like sharing important keys across all queries or chunks of queries, reduce the estimation cost, which allow us to make the whole procedure more efficient. So 2 examples of actually viable dynamic patterns that are considered state-of-the-art nowadays. So on the left, we have the block sparse pattern. So our square matrix, we will first split it into blocks. I think in this case, the block size is 8. And for each block, we'll try to estimate whether this block is important and how important it is for the right approximation of the full attention. So actually, the way how this pattern works is that first we will take our query sequence and key sequence. We will split it into chunks. For each chunk, we'll create a chunk representation, which is created by basically averaging the representations of queries within the chunk and keys within the chunk. Then we'll be computing the dot product between the representations of query chunks and key chunks. And we'll be, for each query chunk, we'll be taking the top k key chunks with the highest dot product. So this is basically how this particular pattern is done, and the estimation cost for this one is n squared divided by b squared, where b is the size of the block or size of the chunk. On the other hand, the other state-of-the-art pattern for prefilling is called vertical and slash. They have slightly different strategy because they're trying to estimate dynamically which keys and which diagonals are most important for a given input, layer, and head. So how do they estimate it efficiently? So what they are doing is they are taking last, let's say, 200 queries. For an input which is 100K, you can take last 200 queries and compute the dot product with all the keys. It's of course much cheaper than like the full quadratic computation. And the estimation cost, the cost of this operation is n times s, where n is the number of tokens originally, and s is the number of this, the number of tokens in this suffix window. So once they compute this dot product between the suffix window of queries and all possible keys, they will aggregate the attention scores that each key token has gotten from this suffix of query tokens, and they will choose top k tokens to keep, and those top k key tokens will be shared for all the queries. So these are 2 examples of how realistically we can deal with those trade-offs. So how we can still dynamically adapt to different requirements of different layers, heads, inputs, but do it efficiently. So both we can do efficient computation after we figure out what to compute, and we also know how to efficiently figure out what to compute. Okay, so we have covered the first 2. Now, 2 still very related and very important parts, but independent from the prior 2 axes. So that is budget allocation and KV cache management. First, budget allocation. This is very interesting because, as I mentioned, again, those attention maps are very dynamic. Sometimes it's possible.
May I ask you a quick question?
Yeah, sure.
So when you have a large number of blocks, how do you deal with the fact that the number of blocks is large?
What do you mean by that? That I deal with the fact that the number of blocks is large?
So if you're dividing n squared by block squared, right? So for each one of these blocks, you have to perform a computation
Yes.
to see whether or not you should pay attention to that, right?
Yeah.
But then you have a large number of these blocks.
Okay, so the crucial thing is basically the comparison of how much this computation will take as opposed to dense computation. So if the dense computation is for a sequence length which is 100K, this is 100K squared if we were to perform the dense computation. On the other hand, like the smallest possible block that was considered by the literature is like, I believe, 16. So in compared to 100K squared, you have, you're dividing by 16 squared, which is basically 250 times faster. So this is what's important. Like this estimation of which blocks you have to compute, this is 250 times faster. So then if you apply 20 times sparsity, so the actual computation, the actual sparse computation will be 20 times faster.
I see.
Estimation cost is 200 times faster. Then you end up being 19 times faster, let's say. So this is what matters.
Thank you very much.
It's not really an issue that, like, for very long sequences, the number of blocks will be large because it will still be much faster than dense attention.
Thank you very much.
Sure. Yeah, and also, like, feel free to interrupt me. I have no issues with that. My main goal is for you is to share my work and share my findings and for you to understand what's going on. So budget allocation. Simplest possible thing basically is to choose a K, like how many blocks, to how many key blocks each query block should attend. Like we can choose that prior to any evaluation. Let's call it like 1,000 blocks. 1,000 blocks is enough. But on the other hand, as we have discussed it, and I will probably mention it many times, all the attention distributions differ significantly across inputs within the model. So they can, for example, be very concentrated or very uniform for the same input, but across different heads. And if you choose a fixed K, then it could be very suboptimal. And if we can come up with a better idea how to allocate budget for a given input, or even within the model for a given input, then we can actually gain a lot. So here's this figure. Let me go through that slowly. So basically, this coloring signifies how a given interaction is important. So like here, for this case, like you can think about that we have 5 key tokens and 2 of them are really important, 3 of them not really. By only paying attention to 2 tokens, we can actually like recover most of the dense attention. In this case, although like this attention is more uniform, and it'd be better if we cover all 4 tokens instead of 3. So the simplest possible approach, like no thinking at all, is that you come up with some budget, it works well on your evaluation suite, you don't care anymore. On the other hand, if we can come up with a better budget allocation, we can adapt to requirements of a given head or a given input, because these attention distributions differ across inputs, then we can not only be more accurate in our approximation, but also more efficient. Because for some inputs, like those attention distributions will be very concentrated. And for those inputs, we can do really, really sparse computation. So one idea, instead of assigning the fixed budget to every possible head, to every possible input, is to, after estimating the importance of particular blocks, we could also like say, okay, so let's look at the distribution of this estimated distribution of importances. And let's take as many blocks until we cover a certain condition. So let's say that we have estimated that instead of tokens, now these are blocks. We have found out that only 2 blocks will should approximate 95% of the attention scores. So we are okay with that. If this estimated the distribution of the importances of different blocks is more uniform, then our target is to approximate or recover 90% of the attention scores. And we see that for this concrete distribution, we need to pick more blocks. So the number of blocks we pick will be now dynamic based on our target that we want to satisfy. And this target that we want to satisfy could be, for example, 90% of the attention scores. So this is how the budget allocation could be either fixed or dynamic. And now the final axis. So that is the KV cache management. This actually only concerns the decoding, because during prefilling it's not an issue. During prefilling we don't have KV cache. Basically, there are two types of methods. One type of method, one category of methods, they, based on some heuristic, they decide that a given token will not be important anymore in the future. And in this case, they can evict it, they can get rid of it, and basically will be saving a lot of memory because of that. So this is very memory efficient. However, the issue is that once a token is evicted, it cannot be attended anymore. Right now, I like this intuition with reasoning models. Like one of the I think core capabilities of reasoning models is to be able to reflect that like a given approach to solve a problem was wrong and choose a different approach. With these type of methods, switching an approach to solve a problem won't be really possible, because when we switch the approach, then a different set of tokens could actually be now important that wasn't important previously. But because those tokens were evicted by this line of work, we cannot no longer attend to them, so our model will crash. On the other hand, some efficient methods, some sparse attention methods for decoding, never evict anything, and they actually involve some memory overhead to still stay efficient, but they preserve this information fidelity and can tolerate much higher sparsity ratios. So this is definitely a benefit, however, in cost of memory. So we have all those trade-offs. And now, okay, so this is the background. This is our overview of sparse attention methods. Now let's get to our experimental setup. How we decided to choose the 6 methods, and how this choice of those 6 methods, what kind of studies and questions it allowed us to answer. So we have chose 3 methods for prefilling and 3 methods for decoding. I believe that those methods that we have chosen are state-of-the-art. And generally, they are considered state-of-the-art. So first of all, we wanted to ablate the impact of units of sparsification. So as I mentioned previously, it's inherently a trade-off. Like there is no that one is better than the other. You need to higher granularity of choice involves higher estimation choice. So you cannot estimate individual interactions. You have to balance this trade-off. So we can compare for prefilling vertical and slash method, which uses, it should be global queries to individual keys, with block sparse method, which uses chunk queries to chunk keys. The same for decoding. We compare SnapKV and Quest. Both has uniform budget. However, the SnapKV uses global queries to individual keys. Then they evict the tokens. On the other hand, Quest can choose a different set of key chunks for individual queries. So Quest, for example, is very flexible method. Then we also compare the impact of budget allocation. So we can do that because we have implemented basically the same method, the same underlying method. They use the same unit of sparsification. They use the same way of approximation of what to compute, but they differ in the way they allocate the budget across models, across the input. And we did it. So we have this comparison for both prefilling and decoding. And we also can ablate the impact of KV cache management. So these choice of 6 methods, they span those axes that we have discussed, and they allow for these ablations. About the tasks, so at the beginning, in one of the first slides, I stressed how much different tasks and really a thorough evaluation is important, so that when we adopt the sparse attention method, we feel certain that it will be robust and it will perform well on variety of inputs. So what we have found in the literature, in short, is that we can consider these 3 axes to really impact the difficulty of a long context input, and also the difficulty of an input for sparse attention. So these 3 axes. The first one is how hard it is to locate necessary information. For needle in a haystack, where we explicitly ask to locate a value for a given key, and also we don't need to do really any work, just copying information after we locate it in the input. This is very low. On the other hand, if the question is multi-hop, if it's more complicated, then this dispersion will be high. On the other hand is scope. So how much information, how many tokens we need to retrieve to be able to answer the question. This is low for needle in a haystack. However, if we have multi-question answering, if we need to summarize the entire input, this will be high. The third axis also, which impacts, as found by prior work, impacts how the structure of the latent representation of the model is whether we actually process the natural data versus synthetic data. So we use 9 tasks. Of course, you can use more than that, which we fully control in terms of sequence length, in terms of also difficulty, and across these 3 axes. So we believe that this is as the best we could do. And the rest of the experimental setup. So we have also investigated the impact of the model size. We used a single model family for a consistent training methodology that used the same training methodology, that is Qwen 2.5 family, so we can understand the impact of the model size. We have tested for sequence length to understand the impact of sequence length, and we have tested those sparsity levels or compression ratios from 1 to 20. First, let me discuss about what we have found about the impact of the model task and about which type of sparse attention method performs the best for a given type of a task. So first, single question answering in natural language. It actually becomes intuitive. Like many of long context benchmarks, single question answering were designed in this way that basically people have taken independent documents and stuck them together to create a very long input, and then ask the question about one of the documents. So basically, if we create a very long input in this way and stack 200 documents, still the question that we're asking concerns only a single document. So we can expect that this type of input, this type of task is highly compressible and also can be highly sparsified. In our case, like single question answering tasks were very easy for all methods that we have tested. Basically, these methods tolerate huge sparsity. I don't know, like we have only tested sparsity levels up to 95%. For all of them, single question answering, basically, there was no performance decline across model size, across sequence lengths. So these types of tasks is fully correlates the added sparsity. On the other hand, if we look at multi-question answering, so what changes now? Basically, previously we had like 200 documents and we only had one question about one document. So we only need to look at one very small specified portion of the input. On the other hand, if we have a very long input, but we have multiple questions, then we need to retrieve very specific information, but from different parts of the input. And we have found, so ruler NIA, needle in a haystack, uses 4 queries. The story retrieval uses 16 queries. We have found that the performance decline, both during prefilling and decoding, correlates with the number of questions. So the more tokens the model has to retrieve, the harder it gets for sparse attention methods to perform well. And this is very intuitive. Like, sparse attention methods wants to compute as little as possible. In our experiments, we make those methods to, for example, compress the computation 20 times. If we have many questions and we need to retrieve specific information from different parts of the input, then after some level of compression, it's no longer possible, so the performance goes down. We have also observed that the gains, so in this particular case, for multiple question answering, actually the methods which uses that compute individual key tokens, which are shared across all query tokens, to perform better than methods that uses chunk to chunk. Why is that? Because what we care about is a small subset of non-consecutive subset of tokens. In 16 questions, we need to retrieve specific tokens from 16 different places. It's very easy if we can choose individual tokens which are important. However, if we were to choose blocks, then sometimes we don't even have the budget to choose 16 different blocks. That's why those block methods are less fitted to this type of task. On the other hand, we have 3 tasks that what we can call them reasoning tasks. So these tasks involve aggregation of information over very long input. You can think about them as summarization, for example. Or like we can have a book with 200 chapters, and basically the question is in how many chapters something happened. So basically we can process chapters independently and then aggregate the answer. For these types of tasks, block-based patterns were much better than patterns that were choosing individual keys. Why is that? Because block-based patterns can choose different set of important tokens for different query chunks. So, for example, for the example of the summarization or the question of how many times a given event, in how many chapters a given event happened, then basically each chapter can be processed independently in the first half of the model, and then the information can be aggregated. On the other hand, the methods which choose individual keys globally shared across all queries are less fitted for these types of tasks, because basically all input is important. We need to aggregate information, we need to check every chapter, and basically there is no budget for that. So this is why, in this case, for these types of tasks, block-based patterns are better. And this has also been proved by many prior work that these types of tasks basically exhibit more uniform attention distributions, which also aligns with this intuition. So this is about like low-level comparison of different patterns. Second, very important main result. What we have computed. So let me discuss this plot. So on the left, we'll discuss the results for prefilling. On the right, we'll discuss the results for decoding. What we have calculated is the maximum compression we could achieve for a given task without performance degradation. So we have used some statistical framework to compute that. It's not that important. Basically, what's in this plot is that for 4 model sizes that we have tested, for 4 sequence lengths that we have tested, individual dots represent what's the highest sparsity we can add to this model, to this task, at this sequence length before the performance declined, let's say, by 5%. What is now the main, three main takeaways from this plot? First of all, we can look at decoding. What happens is that across sequence length, we observe basically no impact of sequence length. Similar compression ratios were possible, and there was like no higher compression ratios tolerable for higher sequence lengths. Second of all, we can achieve higher compression ratios during decoding for larger models. We dig into that deeper in the paper. I won't discuss it at the moment. What is very interesting during prefitting also is that here in prefitting, the model size doesn't really matter, which I will discuss in the next slide because we have developed some intuition for that. What is the absolutely most important takeaway from this slide is that while the average compression ratios that the model tolerates on average, when averaged across 9 tasks that we have tested, are very high. Those are between, I don't know, 12, even approach 20 here. Almost for every configuration, there is a task for which the performance significantly degrades for the compression ratio that's less than 5. This is a very important result. This is the result that says that basically right now you cannot safely apply sparse attention to your model and be sure that it will perform well on variety of inputs. On average, it will perform very well, but there will be some inputs that will be affected. So what's the intuition for that? Basically, the intuition that we have for that is that imagine that we have come up with some measure of the difficulty of a task, and this is the x-axis. On the y-axis, we have the sequence length, and we have an assumption that basically as we increase the sequence length, the difficulty of an input increases. Each dot represents the average difficulty of a task for a given sequence length. And then we have 2 vertical lines, which describe the skill of a model. The skill of a 7B model is this one, and basically it can solve correctly all those tasks. It can solve all tasks for 16K, and it cannot solve anything at 120K. The skill of 72B model is much higher. It can solve all the inputs that 7B can solve, and also some extra inputs that 7B couldn't solve. Now, as we add sparsity to the model, what happens is that the skill of the model decreases monotonically. Basically, our approximation of the dense attention goes down, so the error increases. 72B model can tolerate higher sparsity and still solve every possible input that 7B could solve. However, there are some inputs that 7B couldn't solve, and only 72B could solve. If we add only a little bit of sparsity to 72B, then it won't be able to solve inputs that it could solve with dense attention. That's why we believe there is no correlation of model size to maximum tolerable sparsity. 72B models and larger models are more capable. They can solve harder inputs. And it is indeed true that for very easy inputs, they can tolerate much higher sparsity compared to smaller models. However, there are some inputs that will be affected that are only solvable by those larger models. And now the last and most important takeaway of our work is that we have computed this Pareto front. And we have basically two charts. Performance on the y-axis and the cost of the execution on the x-axis. We compare 4 different models for 2 sequence lengths, 32K, 128K. We plot the performance of each model for this sequence length across different compression ratios. The higher the compression ratio, the more the color goes towards red. So for 32K, what happens is that those dots for different model sizes do not even cross. Why is that? This is because for 32K, the self-attention is still cheap. Right now, we are computing, most of the inputs that we compute are in 32K. But ideally, we'd like to fit all our code base into the context. To do that, we will need 100K, 1 million context. When we move to 128K, the cost of the attention, the ratio that attention contributes to the overall cost of the execution increases. So also the impact of the sparse attention increases. In 28K, the cost of those costs of various model sizes actually begin to cross. And for 128K, already only the sparse configurations lie on the Pareto frontier. So in other words, it's more optimal for longer sequences to use larger model with sparse attention as opposed to smaller model with dense attention. It's cheaper and we get better performance. To illustrate what's going on, basically, here on the left, we plot the ratio of the overall cost that attention contributes and everything else contributes. At 32K, it's 50-50. At 1 million, attention will contribute 97% of the cost of the model. And this is where we are going. Now assume that we try to estimate how much speed up we'll achieve if we add 5 times sparsity to the model. For 32K, this speed up will be still, let's say, low. It will be 2 times. However, as we increase the sequence length, the speed up, the overall speed up scales dramatically with sequence length. As we'll be moving towards longer sequences, we'll be trying to make those models to be able to process long context. Sparse attention will become more and more important. To conclude, I believe after this year of analysis that sparse attention will definitely be key for long sequence LLMs. We won't be able to do long sequence processing with dense attention because the cost just scales too quickly. Second point, there is not a single model or not a single method that handles everything. Different tasks, different inputs have different requirements. They demonstrate different attention patterns. Also, we need to care about this flexibility and estimation overhead trade-off. So, until now, there is still no one-size-fits-all sparse attention method, which basically promotes research into this direction. What I think is the future of sparse attention and what should future research focus on. First of all, we should also be able to choose pattern based on task requirements, because as we have found, different tasks, different units of sparsifications are more fitted towards different tasks. We should also improve adaptive budgeting to be more reliable and robust. First of all, we should come up with a method, ideally, with some theoretical guarantees that will be able to tell us what will be the maximum performance drop for a given sparsity, so that we can control that, so that if we make a choice to equip our model with sparse attention, we'll be able to estimate what's the maximum performance drop. We'll be okay with that. We'll have a clear trade-off, and we'll pick a point, make a decision, what level of sparsity we would like to go for. Or the other solution is to, instead of using plug and play training-free methods, to actually pay an extra cost to adapt the model to use sparse attention to make it training-aware, training-based, such as, for example, native sparse attention that was recently proposed by DeepSeek. And if we have training-based sparse attention, then we don't really need to worry about theoretical guarantees because we won't have this training inference mismatch that is caused by training-free sparse attention. And that's it. Thank you very much for listening. That's the end of my presentation.